Okay, I will show the results of an experimental parametric campaign carried out in in the laboratory LMC2 in our EC in ER in Lyon. And the framework of our research is the reinforcement of historical structure in masonry. In the last years, the use of TRM seems to be the better solution to reinforce this kind of structure, because the mortar give to the composite an high permeability. The mortar is compatible with masonry and give to the system a fire resistance. Another important thing is that this kind of composite is simple to be applied to the substrate. In our laboratory in the last years, a lot of study on masonry have been carried out on the reinforced system characterized by FRP composite. And also in the last 3 years, some studies have been carried out on the effectiveness of TRC strengthening system. In my presentation, I will I named this kind of composite TRM as proposed by the scientific in the last years. Textile reinforced mortar in place to textile reinforced concrete. And our study concerned the textile reinforced mortar characterized by basalt fibers. These fibers are coated in surface. It is an important detail because the coated textile frequently not slip in a telescopic manner inside the composite. The TRM system could be carried out using lime mortar or cementitious mortar. In the last years, in 2016, Ascione, De Felice and De Santis proposed a qualification method to define mechanical parameters useful to the project of the strengthening system. They proposed to match tensile test and shear bond test. The technical committee 250 in the last years work with some research centers, universities, and industrial partners to define the mechanical parameters useful to the realization of technical guideline. Our studies has been carried out to study the influence of the textile density in the mechanical property of a TRM composite. In the same time, we match different series characterized by different kind of mortar to evaluate the influence of this parameter in the behavior of the system. The digital image correlation has been used to deeply study the displacement and strength field on the surface of the specimen. Here you can see the 3 different kind of textile analyzed. T1, T2, and T3, each one characterized by a different number of textile rowing. The T1 is characterized by 3 longitudinal rowing. The specimen of series T2 are characterized by 5 longitudinal rowing, and the textile tree by 7 longitudinal rowing. The experimental campaign has been carried out by tensile test using hydraulic grips to apply the force to the extremity of the specimen. 4 series have been carried out. The first 3 are characterized by the same kind of mortar, but a different amount of textile. The 4th one is characterized by a different mortar and the same textile configuration of the series S2. The textile used in the experimental campaign has been supplied by 5 groups. The mortar used in the study is a gouged mortar, classical gouged mortar, and a mortar, a thisotropic mortar. The gouged mortar is the mortar M1, and the second one is the thisotropic mortar. The experimental setup, you can see the experimental setup in this slide. A camera has been placed at the distance of 1 meter to the surface of the specimen to take photo during the realization of the test. In our case, the algorithm used to analyze the measurement field is the algorithm Corelli, developed by the University of Kashan by the research group of Yield. On the specimen, a speckled pattern of black points on a white surface has been carried out to permit the correlation on the surface of the to permit the correlation. The photos are matched using the algorithm Corelli. A zone of a region of interest is defined in the region of study. This region is subdivided in subzone named ZOE. For each subzone, we could read the displacement, longitudinal and transversal displacement. Here you can see the 3 main failure modes that characterize frequently the tensile test. The first one concerns the failure at the clamps. The second one, the cracking in the length of the specimen. In this case, in the mode of failure 2, a failure of the textile is recorded after the opening of cracks. In the third one, the textile not achieve the rupture, but we have a slippage in the clamps. You can see here the results. In the left, we can see that our results were coherent with a lower standard deviation. On the right, you can see a typical strain stress curve characterized by the first 3 classic phase, the uncracked phase, where the composite work in an elastic manner, and this phase ends with the opening of the first crack. When the first crack opens, a sequence of opening of crack is recorded. We are in the crack development phase. After that, only the textile work, and we can see in the curve an increment of the stress. In our case, we record a failure mode C. We not achieve the failure of the textile, but a slippage in the clamps. The maximal stress recorded in our test is not the maximal strength of the textile, but the stress related to the start of the slippage. If we compare the curve concerning the T1, the T2, and the T3 series here, we can see that in the first, in the second phase, the curve are superposed. The third phase, the three series have a different behavior because each series is characterized by a different amount of textile. It is interesting to underline that in the first two phases, the phenomena are related to the property of mortar. For this reason, the three series, different only for the kinds of mortar, have the three phases similar. The series characterized by a different kind of mortar and by the same kinds and the same amounts of fiber are characterized by two first phase different but similar and a third phase almost identical. If we divide the maximal force by the cross section of the textile, we can see that in the case of the maximal stress achieved inside the textile is achieved in the series T1, where the amount of textile is lower. It is due to the fact that if we put inside the composite, we increase a lot the density of the textile, the mortar of the layer of the upper layer and of the lower layer is not optimal. And the optimal case in the series test is the first one, when we have not a lot of density and the lower layer and the upper layer are homogeneous and the bond between the layers is better. If we divide the force obtained in the first crack, when the first crack happened, by the total cross-section of the composite, we can find the tensile strength of the mortar, and it is logical. The analysis by digital image correlation has permitted to define the displacement field in all the surface of the specimen. And the derivation of the displacement field has permitted to obtain the strain field and to analyze deeply the evolution of the crack during the test. Here you can see that the results obtained by correlation are coherent with the reality. The use of digital image correlation permit to deeply characterize the behavior of the composite, because it permits to obtain the strain between the crack and the exactly the distance between each one of the crack. Concerning the conclusion, the increase of textile density implies a weaker adhesion between the upper and the lower mortar layer. It's interesting in our study also that using a gouged mortar, an ordinary gouged mortar, we could obtain a composite that has a similar property of a composite with a thixotropical, characterized by thixotropic mortar. The digital image correlation could be a useful tool to characterize also this kind of material. Now we are working to carry out Sherborne tests on the same kinds, using the same kinds of composite, but different kinds of substrate. And in line with the ReLAM proposition and protocol, we will compare the result obtained by shear test and by tensile test to obtain the mechanical parameter. And thank you. Sorry for my English. Huh?